Numerical analysis applications commonly require hundreds, thousands, or hundreds of thousands of calculations. The good part is that these calculations are often simple and very similar to one another. Octave, like most programming languages, provides two programming structures to do these types of operations: for loops and while loops. This video introduces for loops. This is the general syntax of a for loop. The loop starts with the word for and ends with the word end or end for. The for statement provides a variable name called var here, an equals sign, and an array. Between the for and the end statements is a block of code that will be executed repeatedly. When the code is executed, the commands inside the loop are evaluated once for every column in this array. Each time these commands are executed, var sequentially takes on the values in the columns of the array. So the first time through the loop, var can be a column vector containing the elements in the first column in the array. The second time through the loop, var contains the elements in the second column, and so on. In the special case in which array is a row vector, each column of the array is a scalar, and var successively takes on the values in the array. Before doing some examples, there are a few notes about for loops that I want to emphasize. You always know beforehand how many times a for loop will execute. The number of times through the loop is simply the same as the number of columns in the array in the for statement. The array in the for statement can be defined by any approach we've used previously to create arrays. This includes explicitly defining each element of the array, colon notation, or any of Octave's built-in array creation functions. For the special case in which the array in the for statement is a row vector, the commands are executed once for each element in the array, and the value of the variable var will be a scalar, and it'll successively take on the individual values in the array. This will probably be the most common use of the for statement in this course. In my first example, I want to determine what the variable y is as a result of this code. Probably the most reliable way to determine the result of a for loop is to create a table that gives the variables created by the loop as the looping structure progresses. In this particular case, there are probably three variables that we want to keep track of: the value for k, index, and y of index. There's also another variable x of k that I could potentially keep track of here, but since it's set directly equal to y of index, I think I don't need to keep track of it. The variables index and x are initialized before the loop starts. So before the loop starts, index is equal to 1. X is initialized as an array. Make sure you've got your array notation straight here. This is the first element in x, this is the second, this is the third, and this is the fourth. So x of 4 is equal to 9. We have to keep track of both the location in the array and the actual value itself. Don't get those mixed up. So now we enter the for loop. The first time through the loop, k takes on the first value in this array. So k is equal to 2 the first time through the loop. X of k is x of 2, which is just the second value in this array. That's set equal to y of index, so y of index is 5. After that, I add 1 to index. 1 plus 1 is 2. I hit the end statement. That takes me back up to the for statement. K takes on the next value in the array. So the second time through the loop, k is equal to 4. X of 4 is the fourth element in the array. That's 9. So y of index is set equal to 9 after the second time through the loop. Index is equal to index plus 1, so 2 plus 1 is 3. Hit the end statement, go back up to the for statement. I get to the next element in this array, so k is equal to 3. The third element in x is 7. Y gets set equal to x of 3, so y of index is 7. Index gets updated to 4. Go back up to the for statement. We're finally at the last element in the array, so the last time through the loop, k is equal to 5. x of 5, x of 1, 2, 3, 4, 5 is 3, so y of index gets set equal to 3. We add 1 to index and end, so this is the end of the for loop. Y is actually set up as an array. We've got array locations here. So when all is said and done, the first element of y is 5. The second element of y is 9. The third element is 7. And the last element is 3. So this is the value of the variable y when the loop finishes. In this second example, I've got a little code that adds up all the integers from the values of a to b and sets the result to a variable named sum. The code starts out by setting values for a and b. These values are arbitrary. The code should work for any integer values of a and b as long as a is less than b. Next, the code initializes a value for sum. I start out by setting sum equal to 0. Now we're ready to start the loop. I can create a vector of numbers starting at a, counting by ones, and ending at b with a colon b. This notation sets an array which for our numbers is 2, 3, 4, and 5. It starts at the value for a, ends at the value for b, and counts by ones. Now, to keep track of what the for loop itself is doing, I'll set up another table. The only values I need to keep track of are k and sum. Before the loop starts, the value of sum is 0. It's initialized right here. The first time through the loop, k is the first element in this array. K is 2. Inside the loop, I add the values of sum and k and set that equal to sum. 0 plus 2 is 2. I hit the end statement. K takes on the next value in the loop. K is 3. I add k to the old value of sum. 3 plus 2 is 5. Hit the end statement, go back up to the for statement, move to the next element in this array. So now k is equal to 4. This adds 4 plus 5 to get 9. That takes me to the end statement. The last time through the loop, k is equal to 5. 5 and 9 is 14. That finishes all the values in this array. I'm done, and the final value of sum is equal to 14, which is 2 plus 3 plus 4 plus 5. Finally, I'll use a for loop to evaluate a Fibonacci series. The first two elements of the series are 0 and 1. Subsequent elements are created by adding the two immediately previous elements. So the next element is 0 plus 1, which is 1. The one after that is 1 plus 1, or 2, and so on. Mathematically, the Fibonacci series is usually expressed this way. For k greater than 1, the kth element of the series, f sub k, is the sum of the previous two elements, the k minus first and the k minus second elements. K is typically started at 0, so the 0th element of the series is 0 and the first element of the series is 1. I want to write a set of code that creates the first n elements of a Fibonacci series and save those values in an array. Before I start trying to write code, I'll usually try to plan the code out a little bit. My preferred approach is to use something called pseudocode. It lists the steps the code will go through without using actual Octave syntax. I first need to set a value for n so that I know how many elements in the series I'm going to create. I also need to set the first two values in the series. The first value, f sub 0, is the first value in the array, so f of 1 is equal to 0. The second element in the array, f of 2, is 1. The loop itself will set a variable corresponding to the kth element of the array. K starts at 3 for the third element in the series and takes on all intermediate elements up to the nth element. The kth element is simply the sum of the k minus first and k minus second elements. I'll implement and execute the code itself as an Octave demo. First, I'll create a script file named Fibonacci. I'll set n equal to 5. Now I need to set the first two values in the sequence before beginning the loop. So f of 1 equals 0, and f of 2 equals 1. Now I can create the loop structure. For k equals 3 colon n, f of k is equal to f of k minus 1 plus f of k minus 2, and an end statement. Octave automatically provides an end for statement to terminate this construction. I'll keep that, but an end statement would work just as well if I felt like changing it. Now I'll save the code and run it by typing the file name at Octave's command prompt. To see the values of my series, I type F. It looks like the first 5 elements are correct, so my code seems to be running properly. However, this code does have a problem. If I go back and set n equal to 1 and type F to view the file, I get the same result I did before. I never cleared the variable f. I'll add a clear statement to my file. Now, if I rerun the program and display the results, I get kind of a strange result. Even though I only want 1 term in the series, I get 2, since there isn't any logic that keeps me from initializing the first 2 elements of the series. I'll go back and add logic that lets me get just the first element in the series if I want. I'll add a simple if statement that allows me to only set the second value in the series and enter the loop if n is greater than 1. Finally, it's irritating to edit the file every time I want to recalculate the series, so I'm going to convert this to a function. My function declaration statement is function f equals Fibonacci of n. Now I need to get rid of the assignment of n within the file so that I don't overwrite the value that's sent to the function. I also don't need to clear the value of f anymore. Since the function has its own workspace, that value will be cleared once the function finishes execution. Now I'll save my function and calculate 6 values of the series by typing series equals Fibonacci of 6. I'll also check that it still works for n equals 1. So I'm going to claim that I'm done now. The process that I went through when I created this file is important, and it can help you when you're writing your own programs. I started out with some pseudocode that outlined the basics of the process. Then I implemented that and made sure that it worked. After the basic code is working, I started modifying it to take into account special cases. Finally, I streamlined the code by changing it to a function. This process of incrementally creating the code, starting with the basics, and adding to that is generally faster and easier than trying to plan everything from the beginning. It's important to keep in mind that for loops are set up to perform the executable commands a predetermined number of times. This is natural in some cases, like when I calculated a certain number of elements in the Fibonacci series. However, in cases in which executions are terminated based on some condition, for loops can be a little awkward, although you can still use them. There's an alternate looping structure that will be presented in the next video, which is called a while loop. This structure continues to loop as long as some condition is met.